In this video, we're going to be looking at techniques that you can use to take the derivatives of the 6 inverse trig functions. Some useful pages in your book to have as a reference would be page 151 that shows you what the formula is for each derivative, for each of the 6 trig functions, and also the page before that, 149, that gives you the principal branches for the inverse trig functions. We're going to be referring to both of those pages. You're also going to want to have the handout that's simply labeled 3.8 exercises at the top. This particular handout, we're not going to do all of it, but we're going to select about 3 problems from here to do, and then use other problems as warm-ups in class and practice. So we are actually going to start today by just reminding ourselves about how the derivative of an inverse trig function might work and the pictures that might go along with that. And the first question that we're going to be working with is actually number 19. So if you want to find that question on the 3.8 exercises page, you're going to see that the directions tell us to do this. They say compute the derivative at the point indicated without using a calculator. So in this case, we are given that y is equal to the inverse sine of x. And the specific point we're interested in is where x is equal to 3/5. We're going to actually come at this problem in 2 ways to see that the 2 answers we get are going to agree with each other. The first way we're going to do it is simply by employing the formulas that are given to us on page 151. On page 151, what you're going to find if you look up d dx of sine inverse of x, you're going to see that that would give us the following derivative. Y prime equals 1 over the square root of 1 minus x squared. That's the formula that we're given, and how would that look for this value? Well, we would plug in x equals 3/5 to get the value at this particular point. So at this point we would say y prime is equal to 1 over the square root of 1 minus 3/5, and the whole thing is being squared. And then we're just going to clean that up a bit. So it's going to be 1 over. And underneath the radical, the second fraction, when we square the top and the bottom, we're going to have 9/25. So keep in mind, I'm just going to think of the 1 as 25/25, of course. And subtract the 2. So I'm going to get 1 over the square root of 16/25. And 16 and 25, as you know, are perfect squares. So 1 over 4/5. When we take the reciprocal of that, we get 5/4. And it's kind of interesting because we can actually come at this problem a different way. Because let's say that you forgot this formula, you could not remember the value of the derivative. Is there any other way to come at this question using what we understand about basic right triangles? And the answer is yes. And it's really useful sometimes to remember that. So we're just going to make a note that the value of the derivative here is 5/4, or 1.25. if we're writing it as a decimal, but we're going to come at it from another point of view. Let's start over and remind ourselves that we have y is sine inverse of x, and x is 3/5. Now, if y is equal to sine inverse of x, then if I write that backwards, then I would say that the sine of y must be equal to x. That's simply by taking the original function that's been defined and writing it without the inverse. It's taking the inverse of the inverse. If that's true, then we could also say that since x is 3/5, the sine of y, whatever it is equal to 3/5. And that leads us to a picture that may be familiar to you. Notice that the 3/5 here is positive, which means that we're limited in this case to drawing a triangle either in the first quadrant or in the second quadrant. Also notice that x itself is positive, so it looks like we're looking at a first quadrant value here. Okay, so here's the basic picture. And remember, just, sine being opposite over hypotenuse, that would mean that if this angle y, reference angle is here, we'd have 3/5, matching up with those 2 particular side lengths. Using the Pythagorean triple, Pythagorean theorem, however you want to look at it, you can find the other leg of the triangle as being of length 4. So a couple of things that we know here. First of all, let's say this is all we knew and we were trying to come at this problem in another way. Well, first of all, we could write all 6 of the important trig functions that we need here. For example, using this picture, I think you'd agree the cosine of y is equal to the adjacent over hypotenuse, or 4/5. That's going to become important to us here in just a minute. Remember that we said that because we have sine y equals x right here, we could, in fact, take this relationship and simply differentiate both sides implicitly. Meaning, let's take the derivative with respect to x on the left and on the right. If we take the derivative with respect to x on the left, we're going to get the derivative of sine, which is cosine y. But since we're taking the derivative with respect to x, we have to multiply by y prime, or dy dx, or however else we want to put it. I'm just going to write y prime. Chain rule. On the other side, we have x. We take the derivative with respect to x, we just get 1. And now if I take y prime and want to get it by itself, because remember that's the thing I wanted to find in the first place, I get 1 over cosine y. Well, I know what cosine y is. Cosine y, we just calculated it for this specific triangle a minute ago, and we found it was 1 over 4/5. Or I'm sorry, it was 4/5. Now we can plug that in and get 1 over 4/5. And if you're having a flashback moment, it just means you were paying attention. Because remember that this is exactly where we were from the previous question. Either way you look at it, we end up with 5/4. We get the same answer both ways. So, number 19 is done. We can approach the other 4 problems in the same set with the same basic approach, and we'll do those as warm-ups later. Let's take a look at another question, which is number 24. And in 24, you have y equals arctan of x over 3. Now, arctan is basically the inverse of tangent. If we simply invert every point on the tangent function, we actually get something that's not a function, because we would basically have all of those arms of the tangent function flipped onto their side, and we would fail the vertical line test. So instead of trying to differentiate this, we need to differentiate tangent inverse of x over 3, which simply means that we're only going to consider this particular function where y is contained in the interval from negative pi over 2 to pi over 2. We're just going to agree that that's the part we're going to look at. Now this is something we can differentiate. The formula for it is pretty straightforward. The format says the derivative of tan inverse is 1 over 1 plus x squared. The only thing I have to remember here is this is still an application of the chain rule. And we have 1 over 1 plus, careful, x plus 3 quantity squared, because that's what our x is in this case. But we also have to remember, this is the step you might forget, to multiply by the derivative of the inside function, which would be 1/3. Now, stop the video for a minute and see if you can simplify this, and then start it up again. Now, what you should get, if you simplified this properly, is 1 over 3 plus x squared over 3. Notice I'm just distributing the 3 across the denominator. Also notice that in the second part of the denominator, I would have had a 3 squared, which one of those 3's would be canceled by the 3 I'm distributing. So there you have it. Last question I want you to try, actually try this one, stop the video here just a minute and try it yourself, is actually problem 27. And this one is one you're going to need the product rule for because it is a product. So here is your problem. Take a moment, stop the video, try it out, and then check your answer. Okay, so here's the solution. As you can see, I just applied the product rule to both parts, and then combined a few, not really like terms, but basically just went ahead and did the multiplication and tried to make it as neat as I could. This one is not particularly neat. So hang on to this handout, the 3.8 exercises, and we'll be coming back to review this a little bit as we prepare to move on and take integrals of these particular types of inverse functions.